Hello everyone, thanks for following our talk. My name is Federico Maggi, I'm a researcher with Trend Micro, and I'm here today with my collaborator Marcello Pogliani, who just received a PhD from Politecnico di Milano. This research is based on a joint work between Politecnico di Milano and Trend Micro Research. 3 years ago, we were here on the Black Hat stage, where actually we were in Vegas, but still, we were on Black Hat, explaining to you what were the risks of having an industrial robot connected to the factory network. We showed you several ways that an attacker can abuse a connected robot, and we show you the impact of real attacks. For example, they can introduce micro defects into the production. 3 years later, we are here once again, but this time we talked to you about programming of industrial robots. We examined 8 of the leading industrial robot platforms, and we found some design issues that can have an impact in terms of vulnerabilities that could be introduced by mistake by developer. And on the other hand, we showed you how a malicious actor can use these languages, these custom languages, to create new strains of malware. Last, we will conclude our presentation telling you how we can prevent vulnerabilities, and in case we cannot prevent, we show you a technique that we have developed to detect vulnerabilities and malicious code. So let me now hand it over to Marcello, who will explain to you how industrial robots are programmed.
There are 2 different ways of programming industrial robots. The first is called teaching by showing and is about programming a robot while moving it using the teach panel. That's a device you can find on this slide. This is a very interactive and online way of programming robots. On the other hand, for more complex tasks, you want to use a full-fledged programming language to program a robot offline. As this talk is about programming languages, let's see how they look like. Here you can find a simple task program implemented for ABB's rapid programming language. This program moves a robot between 2 points, point 0 and point 1, repeatedly in a loop for 10 times. As you can see from the source code, it's like having a general-purpose programming language with the addition of robot-specific instructions and data types. The same concept can be applied to different languages. Here is the same program implemented for another language, QCascadR. As you can see, the structure is very similar. I'm using the terms language and vendor in a pretty much interchangeable way because in the robot space, languages are mostly proprietary. To program a robot of a certain vendor, you must use the proprietary language, the proprietary domain-specific language of that vendor. So to say to program an ABB robot, you must use a REP. There isn't any cross-platform language or lingua franca that can be used to program robots by different vendors. Back to the topic of our talk, we analyzed the languages of 8 different vendors in order to see if they had security-sensitive primitives. So to say, primitives that can be used to bypass security boundaries. The first primitive that we analyzed is the ability of reading or writing from the file system of the robot, directly from the task program. This capability is present in 5 out of 8 programming languages, and well, it's not exactly surprising because there are a lot of use cases for this, such as writing log files or reading coordinates from a file. The more advanced file systems have also the capability of performing directory listing because they are hierarchical, not just a flat list of files. More surprisingly, we found that in 4 cases, it was possible to load new code at runtime. So the language is exposing primitives to load a module, to load a code module from a file, and to dynamically resolve a function name at runtime and call it, and call the function with that name. This capability, combined with the fact that it is possible to write on a file system, makes it possible, if the language is interpreted and not compiled, to write programs that write a program, load it, and calls it. So to say, having some sort of writable and executable memory area. Last but not least, we found that all the languages that we analyzed have the capability of performing network communication. So to say, to use network sockets. Before going forward, I would like to give a short look at the runtime environment if we consider modern platform, the tendency is to have third-party application to be isolated, to be sandboxed. If an application is to access resources from the operating system or from the hardware, that access is mediated. It's mediated by an access control mechanism that is fine-grained and application-specific. So I can have an application that doesn't have the permission of access the device system, or I can have an application that has the permission only of accessing some subset of the device system. In case of industrial robot, it is not so. There isn't any access control mechanism for task programs. Programs run in an unrestricted way. If there exists an instruction or an API to access a certain hardware resource, that resource can be accessed by all the programs.
It turns out that the features that Marcello just explained to you are actually used. We talked to about 20 experts, including developers, control process engineers, as well as some academics working in the field of robotics. And they all told us that in one way or another, when they develop code to automate a robot or an industrial machine, they need to use network features such as network sockets, they need to use file operations, they need to use dynamic code loading, and some of them told us that their software, the automation scripts that they come up with, are complex enough to need subroutines in order to structure them in an elegant and usable way. We also wanted to understand how much awareness there is in this community, how much security awareness there is in these communities. The percentages that you see on the right-hand side of the screen indicate the fraction of conversations going on in the major online communities for industrial automation engineers, which contain security-related terms. We searched about 12 of the most active forums looking for conversations containing keywords such as hack, security, vulnerability, fixes, patches, and stuff like that. And we found that only a minority of the conversation are about security. In some cases, there is even almost nothing about security in the forum as well. So to summarize what we have so far, we have a fairly scarce security awareness, at least according to the data that we have collected and to the interviews that we have conducted. We have industrial machines that are programmable using these legacy programming languages, which are makes it fairly difficult to switch away from because every vendor has their own technology. And these programming languages include security-sensitive features, which may impact the security of any produced automation program. And last, very important, we found out that there is almost no security isolation. There's no resource isolation that is fine-grained enough to avoid, for example, that if a program contains a security-sensitive operation, the operating system may or may not be able to block the execution, or at least ask for confirmation upfront to the operator. There's no such features that we have found. So you may ask, what could possibly go wrong? Well, on the one end, developers may introduce vulnerabilities by mistake because they are not aware of the security implication of using those security-sensitive features. And on the other hand, threat actors may use these powerful features to develop new strains of malware. And we found evidence of both cases. On the one end, we found public code containing vulnerabilities. We found industrial automation code in GitHub and GitLab and other repositories, and we found vulnerabilities in there. And on the other hand, we were able to prove that these languages are powerful enough to allow malicious actors to develop fairly advanced malware. For example, we developed a malware with self-spreading capabilities and file dropping capabilities, so remote updates essentially. Let me now switch it over to Marcello again, who will explain to you the first part, vulnerabilities.
Vulnerabilities in industrial robot programs happen because of two ingredients. The first ingredient is related to the fact that the programming languages used for industrial robotics have security-sensitive features, just like the ones that I showed you before. The second ingredient is related with the fact that sometimes task programs lack appropriate input validation, which is partially related by the lack of security awareness among who programs industrial robots, as Federico showed before. So overall, it's possible to have vulnerabilities because the combination of those two ingredients makes it possible to have vulnerabilities in task programs. And actually, we found vulnerabilities in some real task programs that we found out in the wild. We found various instances of vulnerabilities, unrestricted movement commands, path traversal, and unrestricted function calls. So let's start with the first class of vulnerabilities, unrestricted movement commands. This vulnerability is mostly found in motion servers. So motion server is basically a program that allows a robot, that allows the motion of a robot to be controlled externally from the network by an external party. So it's basically a program that receives a movement command over the network and translates it in one or more movement instruction and issues them down to the robot. This pattern is mostly found whenever we want to integrate a robot, an industrial robot, with an external system, and we want that external system to directly control the motion of the robot, and there isn't any supported official way of doing so. So we build a motion server, and we control the robot through that. Indeed, we found motion servers among adapters for ROS Industrial. ROS Industrial is a project aimed to bring compatibility between ROS and industrial robots. ROS is the robot operating system is the most widespread and well-known open source middleware for robotics, not just industrial robotics, but robotics in general. In this slide, you can find the main GitHub project page for QK Experimenter, which is the adapter for ROS Industrial for QK robots. This adapter is basically a motion server. It's written in KRR, which is the QK language, and it's written as a test program. So what is the big deal with unrestricted movement commands? So if we don't have input validation in the test program that implements a motion server, and if we don't have any form of authentication, and this is the case of basically all the motion servers that we found in the wild. If we, in this case, an attacker that has access to the same network of the robot can basically control the robot arbitrarily, which is not necessarily a big deal from a safety perspective because there is the safety system. And indeed, even if there is the safety system, it's never a good idea to bring the robot close to the safety limits. Just to give an example, when we were working on this research, we were controlling a robot with a ROS adapter, with a ROS industrial adapter, and by doing so, we ended up hitting the safety limit quite fast, and our colleagues had to send the robot for maintenance. So we broke down the robot. The best thing here would be to perform input validation. Input validation by restricting commands that are for sure, for knowledge that it is possible to have and to embed in the task program, not allowed for that specific work by the robot. It would be also nice to add authentication. Also for how the robot languages work, it's not straightforward to add authentication. For example, it is not possible to have cryptographic primitives in most cases. This is a vulnerable motion server. So let's go to some code, and this is a vulnerable motion server. The function EKI get real is taking in the KRR language is taking a real value, a floating point value for a network, and saving it in a variable. We do the same for all the 6 components of the coordinate. We end up with a coordinate, jump position command, and we move the robot to that coordinate. PTP is basically move the robot, it's point to point. And we do this in a loop. So it is basically a bare-bone motion server implemented in KRR, the QK language. The second class of vulnerability is directory traversal. So directory traversal works just like directory traversal works in other cases. We have a program that opens a file whose file name is controlled by data received from the network without any form of validation. So for a network, we send a file name, the robot controller opens that file, reads it, and sends it back over the network, or writes it, or does something with that file. If there isn't any form of input validation, an attacker can send a file name with the usual pattern / and traverse the hierarchy of the file system, ending up reading, for example, secret information. This is a bare-bone example of a server that is vulnerable to path traversal. With the circuit receive function, we receive some data. We pass from that data a file name, we open a file with that file name, and then we read it and send it back over to the same socket. This example is in the rapid programming language, which is the ABB programming language. This might seem like a toy example just for the sake of making an example. Actually, we found the same pattern implemented into the real world. So some years ago, we found in the robot app store by ABB this web server implemented in Rapid, which was intended to serve static and dynamic page from the robot directly. You could have, for example, dynamic page including variables, including rapid variables. So you could have a very nice status page served directly from the robot, which is a good use case. The problem is that this web server had a straightforward path-traversal vulnerability that allowed to traverse the hierarchy on the file system and exit from the web server root. So from the web server root, it was possible to exit from there and read files on the root on the file system of the ROM. So for example, secrets.txt, just to make an example, but it was possible to read sensitive configuration files or anything else that was present on the ROM. Last but not least, input validation on function calls. So let's suppose that we have a program that allows to perform different operations according to data received from the network. So start cycle, stop cycle, operation A, operation B, operation C. Instead of using a switch statement, we can implement this as doing a late binding or call by name function by calling a function that corresponds to the functionality received from the network, and that name, composing that name of that function with the data received from the network. So if we want to call the operation start cycle, the network will send, I will send function start cycle. The problem with this is that it is possible for an attacker to call any arbitrary function, defined in the file scope or in the system scope. Well, this depends upon the language, but basically the attacker can make the robot call any arbitrary function. Well, of course, the remediation here, it's pretty simple. It's just to implement an allow list of the functions that are deemed valid. This was all for vulnerabilities, so let me now hand over to Federico, who will talk about using languages for malicious purposes.
What do we need to write malware? First of all, we need network capabilities, and we showed you, Marcello just explained to you that we have in all of the languages communication capabilities over the network, and we also need some file exchange, file handling capabilities. And for example, if we combine these two, we can create a malware that, I don't know, exfiltrates files, right? So we have the features there. Secondly, we need the ability, if we want to develop some advanced malware, we need the ability to load code that is only available at runtime. And we've seen that we have, in most of the languages, we have the capability to load code in memory, in the robot's memory, and then jump to it. Third, we need to be able to scan potential new targets over the network. So we need a port scanner essentially. And at least on paper, we have all the features that we need as well. And last, we need a Turing complete language, which means that we need to have conditional statements such as if then else, and also we need loop statements such as while or for. And in all of the languages that we have analyzed, we have those features. For example, here is a network scanner, a port scanner that we have developed using the ABB Rapid language. We used ABB only because we had all the programming environments available, not because ABB has some specific features. All of the languages that have the same features, according to our tables, can be used in the same way to develop the same malicious capabilities, essentially. We also attempted to develop, and we succeeded to develop a file harvesting routine. You see here that the code is going down the file system tree and is exfiltrating the full path of the files, but we could even exfiltrate the entire file content over a network socket. And what you see here is a simplified structure of a malware dropper. that receives data from the network, writes that data onto a file, and then loads that file into the robot's memory, and last points the program pointer to the main routine of that loaded code. So I want to show you a little demo of what happened when we put all of these things together. What we have here is a 3-station robot. All of them are vulnerable. They run a vulnerable server, but only the first one is exposed to the network, to the external network, and is running an infected version of that server because the attacker has already compromised. As you can see, the other two, controller 2 and controller 3, are not running a vulnerable version. So it's not, I mean, it's vulnerable, but it's not infected, sorry. So now we start the, for example, we can do a port scanning routine using the first robot to scan the internal network. So maybe we find the other 2 robots. There it is, first robot found, second robot found. And now the attacker can start the propagation routine, which will attempt to use the open port on the second and third robot to propagate and try to infect their files as well. Notice that we can have the robots doing normal tasks, and you wouldn't notice anything in their motions. I mean, the underlying server is running in parallel. It is not affecting the execution of their movements. And meanwhile, you can see on the console, on the black console on the right, that the propagation is continuing. Now it's finished. So now we can go and check what happened to the other 2 robots. Just for confirmation, robot number 2, now the file is infected. Notice that the IP address has been retained. And the third one is also infected, retaining the IP address. Okay, so this was just to show you that it is possible. Good. So in addition to having a remote code execution vulnerability, as we have in the first robot on the left that you just saw, in order to bootstrap the infection, the attacker may also be a little bit more creative. And I want to spend a few slides explaining to you this. We found out that some of the robot vendors provide an ecosystem that is very similar to our app stores that we have for mobile phones. And they use these app stores to deliver software that will either run directly on the robot or on the machine, or that will be used to enrich the functionalities of the development environment. So you download, for example, plugins and stuff. But the interesting thing is that for some vendors, this is integrated into the development environment. So you can go and have a true app store experience, find the apps that you want, one-click install, and those will be downloaded either on the robot or directly on the development machine, on the engineering workstation, so to speak. Among all the stores, we think that ABB's is the most advanced one because it really has all of the features of an app store. You can go and register and upload software. For our security analysis, what was important is that we reported a vulnerability that ABB has fixed, but we would like to use this vulnerability to show what could have happened if that vulnerability wouldn't be fixed. The vulnerability is on the back end, so you don't have to do anything if you're using ABB software because ABB has already patched the vulnerability on the back end of their app store. So according to that vulnerability, an attacker will be able to upload a malicious application, a malicious code, and have it immediately available for download. You can see on the right-hand side of the screen that on the development environment, that extension that we have uploaded as a test was already available. Whereas if you notice on the left, the application is still pending for approval. So due to this bug, it was possible for an attacker to completely bypass the approval procedure. We also wanted to see if there was any human approving the extensions. So we uploaded a test extension, a test application containing a very clear banner saying that such extension, such application shouldn't be considered because it was simply for research purposes. And so we wanted to see if there was anyone there reading the content of our pop-up that will appear immediately after you execute the application. And as you can see on the left-hand side, the application got approved despite this warning. We found a variation over the same issue, but I don't have time to go through it, in the KUKA platform. This time we had to, we released an alert through the ICS cert because there is a fix that must be applied on the client side. So if you're using the KUKA platform for developing a robotics application, make sure that you run the last version because it contained the patch.
Let's go back to vulnerabilities. The vulnerabilities that we have considered so far depend upon the fact that there is some input which might be untrusted and untracker controlled in a test program. This input will end up influencing some operation in the robot with a concrete input, such as moving the robot. So basically what we're talking about is taint-style vulnerabilities. Generally speaking, we have a taint-style vulnerability whenever we have an unsanitized data flow between a sensitive source and a sensitive sink. In all the languages that we have considered, there are multiple functions or instructions that can be considered sensitive sources because they allow external data to reach the program. Such functions are file handling, inbound network communication, and functions that allow to get data from the user interface of the teach panel. All the languages also have other functions or instructions that can be considered sensitive things, such as functions to move the robot, function to handle files, function to write the configuration, and function to perform changes in the contraflow of the program, such as call by name and late binding functionalities. Given this context, we implemented a prototype of a static source code analyzer for programs written in industrial robot programming languages. Our analyzer is able to analyze the source code of a task program and to find potential taint-style vulnerabilities or potentially abused features that can be expressed as a data flow between a source and the sink. Our analyzer works in this way. We start with the task program source code, we parse it with the appropriate module for the language that the program is written into. We have implemented rapid and KRL parsers. We build the abstract syntax tree and the control flow graph. We build the control flow graph in a way that is language agnostic, and from the language agnostic control flow graph, we link them together. We link the control flow graphs of every function together into the interprocedural graph, and we run the analysis, the data flow analysis on the interprocedural graph. The data flow analysis is configurable with respect to which functions and instructions to consider as sources, to consider as sinks, and to consider as sanitizers. In this way, it is possible to find potential taint-style vulnerabilities by configuring the data flow analysis engine with the source and the sink that we have seen on the previous slide, as well as to find potential abuse features. Okay, that's enough talking for now. Let's now switch over to a very short demo of our tool. So I would like to start with the analysis of a very simple program written in KRL. So the program works in this way. Here on the line 72 and 73, you can see that the line 73, we are moving the robot with a PTP point-to-point movement instruction to this coordinate, joint position target. This coordinate is this parameter that is passed to this function, and it's an output parameter. So this is written by this function. So let's see what this function does. And we can see that this function uses the EKI-getReal function to get data from the network and writes it into this joint position command, which is given as an output parameter. So basically, this is a motion server. Let's see what our analysis tool has to say. So our analysis tool outputs a JSON file with the results of the analysis, which is basically a list of source-sink pairs that correspond to the found data flow, to the found patterns. In this case, we have found just one pattern with one sink, which is this sink here, the PTP at line 73, where the tainted variable is joint position target. This sink is tainted by multiple functions because all these 6 EKI-getReal are tainting the variable joint position command. So we are finding that in our sourcing pair, we have multiple sources and one sink. Okay, at this point, we can analyze a more complex case, which in this case is written on Rapid, and it's basically the web server that we found some years ago on the Robot Studio Robot App Store. The one that was vulnerable to a path traversal vulnerability. In this case, there are 5 patterns, 5 different patterns. If we go and see the first pattern, which is this one here, we have that this is a pattern between the source at line 126, socket receive, variable rect bytes, and the sink is this open here at line 567, which is in the function send files. Let's take a sneak peek at the source code of this program, and we can see that the function at line 126 is this one. So here we are doing a socket receive, and believe me, this is receiving the data of the HTTP request from the client, saving it in the rect bytes variable, parsing it and doing stuff with that. And line 567, we have this opening the function send file, which is taking the file name which comes from the parsed request from the client, opening the file and sending it back to the network circuit. So basically we have a part of as vulnerabilities, as we expected. We have other patterns that are related, for example, to the function that does the same thing, but for dynamic files, not static files. Anyhow, now that we have this tool, that we have the ability of analyzing programs, what we do with that? Well, what we do is to take a data set of programs, of real test programs, analyze them and see if there are vulnerabilities in them and how much vulnerabilities are widespread. Unfortunately, this is very difficult to do with test programs because robot programs are highly sensitive intellectual property, and it's very hard, if not impossible, to find public code. So as a proxy for real test programs, we found about 100 files, rapid and KRL files on public repository on GitHub and GitLab, and we analyze such files. So such 100 files are only files that have at least one sensitive source, so that they at least take some input from an external source, because otherwise there is no vulnerability of this kind. We analyze such 100 files. They are mostly educational files, teaching files, or demonstration projects, and we use them as a proxy for real test programs. So what we found? Vulnerabilities. We found 2 projects with a vulnerability that allowed to execute arbitrary functions. We found 1 project with a path traversal, and we found 13 projects that allow to specify arbitrary movement from data received from the socket. Of course, our tool is not perfect, far from being perfect. We found also detection errors. Particularly, we found a false negative in the analysis of the RAS industrial adapter for Rapid. It was implemented as 2 different test programs that run concurrently and that talk together by means of interrupts and shared memory. Our analyzer is able to analyze the content flow graph and is not able to detect implicit data flow between different programs that communicate via other means.
In addition to using the detection tools that Marcello explained to you, another important thing to consider is to prevent vulnerabilities in the automation code. This means that we need to implement secure communication at the application level. In turn, this means that the OEMs should consider having strong implementation of cryptographic primitives right into the languages. Not all of the languages implement them now. Maybe it's not needed right away, but in the future it will be needed because robots will be more and more connected. Secondly, another important thing is to consider input validation. It is challenging deciding what to do when an automation program receives invalid input, because we have a moving object. A robot is a moving object, moving physical object. So if the robot is already in motion, for example, it is not automatic to decide what to do if we receive a coordinate that is off the safety zone, for example. That's why it's very important, if we cannot implement input validation, to have a safety system configured properly, because the safety system will essentially implement input validation in the physical world, so to speak. Privilege separation, the implementation of privilege separation, I think will be a true game changer, because it will change the way developers create these automation programs. It will force the developers to declare when they have to use security sensitive primitives, such as network, file, or using dynamic code loading, pretty much like we do when we develop an application for a mobile phone. We have to declare all of the permissions. And at deployment time, an operator will have to go through the checklist and decide whether or not that application is good for the setup, the network, or whatever is running onto. Last, to mitigate the spread of malicious code, I think that in the future we will see code signing. It will take probably 5 to 10 years, I think. We'll see code signing implemented also on these platforms. To conclude, working on this project was brought me back like 20-25 years ago, when the first vulnerabilities in web applications started to come up, and people were started to exploit them. And as you have seen, I mean, the classic example of the path traversal is really an example of a vulnerability that is classically found in web applications. And I think that in this space, there are more and more vulnerabilities to uncover. It's simply that we're not looking on that languages now. Secondly, the most important point is resource isolation. I want to stress this one. It is important that the future languages include some ways to differentiate between security sensitive and non-security sensitive instructions, so that the runtime can decide what to do at execution time. Third, we ask automation engineers to please read through the security guidelines that we're going to release as part of our research paper. And last, security officers, please start to think on including these weird and custom languages as part of your code reviews activities. To conclude, please stay tuned, because in a few weeks we will release a paper with the full details of the detection system that Marcello has explained to you, of which we have a prototype. So if you have ABB or KUKA code running on your systems and you would like to have that code checked, please reach out. And thanks for following our talk. And last, security officers, please. Hi, everyone. Just wanted to say greetings from Italy. I don't see any questions, unfortunately, but I can understand why. We're competing with some great talks on the other tracks. Just wanted to say that it's still very cool to attend and talk to Black Hat, even if it's a bit different. So I really hope to see you all next year in real Vegas. Thank you very much, everyone. If you have questions, we're going to stay here for the entire Q&A time. If Marcello has something to add.
No, I don't have anything to add at the moment. We have put on the chat room some links to our papers and to.
Wait. Somebody is asking. Alex is asking. Did you ask any vendors / publishers, for example, code to analyze? Finding code is hard, and I don't think that asking vendors. I mean, we tried. We cannot really disclose whom we asked to, but I think the best to ask is system integrators, because they produce most of the code. But unfortunately, it is highly sensitive intellectual property. So the answer that you get is, in the best case, yes, let me find out, and then they will never get back to you. So if, of course, any of the people who have attended have any contacts with system integrators or producers of industrial automation code, especially if written in ABB or KUKA language, because we have the analyzer ready, we will be very happy to connect with this. Yeah, thank you, Jake. Okay, no more questions. Make sure that you check out the paper at the link that we provided.